Hey everybody. So this lesson is on coiled conductors. So it says to describe qualitatively a moving charge as a source of a magnetic field and predict the orientation of a magnetic field from the direction of motion. So it's pretty much what we were doing before the break, but this time it's with a coiled conductor. So here's a little video that will help you just review that first left-hand rule. And I know it's a little bit cheesy and it's okay to make fun of it, but Deirdre will guide you through this. So there you go.
So Anthony, you're a musician.
Well, I'm not a professional or anything, but I like to play.
There's a lot of physics involved in music, including electromagnetism.
Electricity and magnetism in music?
It's a crucial combination for speakers.
I might have to fix one day. So how do they work?
Okay, let's start at the beginning. Deirdre, what are some of the similarities between static electricity and magnetism?
Well, there are two types of electric charge, positive and negative.
And two types of magnetic poles, north and south.
Okay.
The two types of electric charge and the two types of magnetic poles interact with each other in a similar way.
In what way?
Well, opposite charges attract, and like charges repel.
And the same thing goes for magnetic poles. Like poles repel, opposite ones attract.
You're doing well. Any other similarities, Anthony?
Well, electric and magnetic forces are both action at a distance forces.
Meaning?
Meaning charged objects set up electric fields and magnetic objects set up magnetic fields in the surrounding space.
And both decrease in strength the farther you get from the source.
Anything else?
Well, certain substances can be electrified by rubbing.
Such as your hair or a balloon when you rub them together.
And certain objects can be magnetized in the same way.
Good job.
In the early 18th century, reports began to appear that lightning changed the magnetization of compass needles and made magnets out of knives and spoons. Accumulated evidence suggested to scientists that perhaps electricity and magnetism were related. In fact, they might be two components of a single phenomenon. However, no link was found, and by the beginning of the 19th century, it was generally accepted that electricity and magnetism, although similar, were separate and distinct phenomena. But in 1819, Hans Christian Ørsted made an unexpected discovery which dramatically changed the course of science. Ørsted, a Danish physicist, found concrete evidence for the relationship between magnetism and electricity while lecturing at the University of Copenhagen. By one account, Ørsted was trying to show that magnetism and electricity were not related. He placed a magnetic compass directly beneath a long conducting wire. The wire lay along Earth's magnetic field lines, so that the compass needle was naturally lined up parallel to the wire. When Ørsted connected the wire to the terminals of a battery, to his surprise, the compass needle deflected toward an east-west orientation, nearly perpendicular to the wire. Ørsted had discovered what is now termed the basic principle of electromagnetism. Whenever an electric charge moves through a conductor, a magnetic field is created in the region around the conductor.
So, what did Ørsted stumble upon, Deirdre?
That a magnetic field exists around a current-carrying conductor.
Right. Now this summary chart compares the characteristics of gravitational, electric, and magnetic fields. Let's complete the chart by adding the source of each field.
Okay, a gravitational field surrounds any mass.
And the source of an electric field is an electric charge.
Right.
And the source of a magnetic field is an electric current.
Or any moving electric charge. Right.
So how does the speaker work?
Well, we've got a cutaway of a speaker here, and it's fairly simple. There's two magnets. There's the permanent magnet and the electromagnet, which is attached to the voice cone. And as energy is passed, electric current is passed from the amplifier through to the electromagnet. It sets up two separate magnetic fields, which causes the voice cone to respond and to move the cone, which causes the diaphragm and the speaker to move, and that's what pushes the air that causes the sound waves.
What? Sounds simple enough.
So what happens if we reverse the connections to the power supply on Ørsted's apparatus?
Try it.
Wow, the compass needle deflects in the opposite direction.
Why?
Well, how do we define the direction of a magnetic field?
That's the direction the north pole of a compass needle would point when placed in a magnetic field.
So when the current through the wire is reversed, the compass needle points in the opposite direction because the magnetic field around the wire switches direction.
You've got it. It was a French physicist, André-Marie Ampère, who continued Ørsted's work.
I take it he used this stuff?
Yes, he used this stuff to determine the characteristics of the magnetic field around a straight conductor. Now it's your turn.
So, where do we start?
Well, the first thing we do is send a current through the straight wire to set up a magnetic field around the wire.
Right. But don't turn on the power supply until after you've finished your setup. The wire draws a large current and becomes dangerously hot if it's connected too long.
Okay.
So then, we can figure out the shape of the magnetic field lines by moving a tiny compass around the wire.
Right. The compass will align with the magnetic field lines.
Okay, turn on the power supply.
So, what do we have?
It looks like the magnetic field lines are circles around the conductor.
And, as the distance from the wire increases, the compass needle aligns more slowly.
Which indicates?
It indicates that the field gets weaker as the compass moves further away from the conductor.
Well, one of the really key issues is the quality of the magnets that are used in the components of the speakers, as well as the engineering, and this is what sort of differentiates between a high quality speaker and one that is not regarded as a top of the line type speaker.
Well, how is that important?
Well, there has to be really close tolerances in the air gap in here, and you know, the more quality speakers have much closer and tighter tolerances, and this is what makes a difference.
So, you can increase the magnetic field, but still get a smooth response.
That's right. It's the smoothness of the alignment and how well everything works together.
Would reversing the direction of current flow change the shape of the magnetic field?
Well, it would change the direction of the magnetic field, but I don't think it would change the shape.
Try it.
Nope.
The shape didn't change, but the compass needle did swing in the opposite direction.
Okay. Now how about increasing the amount of current through the wire?
Well, the shape of the magnetic field lines didn't change, but the compass sure snapped to attention.
Excellent. The torque on the compass needle indicates the strength of the magnetic field.
Cool.
So, you've determined the shape of the magnetic field lines around a straight wire. You've also discovered two factors that influence the strength of the magnetic field.
The larger the current, the stronger the resulting magnetic field.
And?
And the strength of a magnetic field decreases as you get farther from its source.
Well done.
André-Marie Ampère introduced the concept of current flow as charge per unit time. The SI unit of current, the ampere, or amp, is named after him.
Anthony, put out your left hand.
Okay.
We've just seen that a compass needle can indicate the direction of the magnetic field lines, but there's a shortcut for determining that information too.
And it involves my left hand?
It sure does. Deirdre, In which direction does current flow?
From the negative terminal to the positive.
So in this case,
Is from here to here.
good. Now Anthony, grab the wire with your left hand so that your thumb points in the direction of current flow.
Hey, cool! My fingers point in the direction of the magnetic field.
Right.
Weird. The ribbons attract.
Now, if I reverse the connections,
They repel.
What's going on?
try to think of each of the ribbons as a single straight wire conductor.
Does it have something to do with the direction of current flow through each ribbon?
And the magnetic fields that result?
Look, suppose the current flow through each of the ribbons is in the same direction, say down. What would the magnetic field lines look like?
Using the left-hand rule, the magnetic field lines around this ribbon look like this.
Do both ribbons.
I'm out of left hands.
I have one. Do you see the answer in the diagram?
Not yet.
Okay. What about now? What if I add the polarity of the magnets?
Oh, those are magnets.
Okay, I get it. When the currents are allowed to flow in the same direction in the two ribbons, the magnetic fields between the two ribbons are in the opposite direction.
So the ribbons should attract, because opposites attract.
Good thinking.
Okay, so here's a little diagram of a coiled conductor. When straight current carrying conductor is coiled into a loop, inside the loop the B fields are all aligned. Remember that B fields are magnetic fields. They're all aligned in the same direction. So this makes a stronger unified magnetic field. So if you take your left hand and point your thumb in the direction of the arrow on top, that's the direction of the current, you can see that inside your fingers are all pointing in the direction of the diagram, right? So what it does is it makes a bar magnet that just coils around it like that. So each coil works like a tiny magnet, and if you add more and more coils, it's just like adding more and more magnets, and you get a stronger magnetic field. Now when you take a look at this picture as a whole, what does it remind you of? It kind of looks like a bar magnet, right? It kind of looks like the fields of a bar magnet, just like we were doing before the break. So current carrying conductors containing large enough coils are called solenoids or electromagnets. So you may see those terms show up on a test. What you get is you get a strong invisible bar magnet inside the coiled loops, and you can find the direction using the second left-hand rule. That's what we're going to practice in a second. So solenoids are used instead of straight conductors when you need a large field, because the more loops you have, the stronger your field you get, as opposed to a straight conductor where you're kind of stuck with that one line there. So we're going to take a look at this simulation here. Just let me open that up. Just let me find it here. There it is. So here is our bar magnet that we did before the break, and you can see that the north end of my compass is pointing to the south end of my bar magnet, right? And then opposite, the south end of my compass is pointed to the north end. So our magnetic field runs from north to south in that circular path. So if I do the same thing with an electromagnet, you can see that it runs from north to south, right? And because here's the south end of my magnet, here's the north end of my magnet, right? The north end of your magnet, the red end of the compass, sorry, is the direction of your field. So you can see that this must be my south end over here, and this is my north end over here. So it runs from north to south. And if I switch the direction of the current, you can see that, oh, look, my compass flips. So now my north end is pointing over here, which means that south, and my south end of my compass is pointing over here, which means that north. So it still runs in that loop sort of shape. So electromagnets can have an air core, or they can have a magnetic material such as iron inside. And it doesn't really make a difference. It doesn't increase your field. It just sort of helps concentrate that magnetic field within the iron core. So here's our second left-hand rule. So a coiled wire works just like a bar magnet, so we treat it just like a bar magnet. So the second left-hand rule is used to find north-south of an electromagnet. So there's just two things. So your fingers are the coils, and the tips of your fingers are pointing in the direction of the current. So you can see that here's the tips of his fingers, and it's pointed in the direction of those coils right there, the direction of the current in the coils. And then the other part is that your thumb is the direction of the north end of your bar magnet. So this is north, this is south. So we can draw on our field lines, and our field lines run from north to south like that. So let's do an example. So what I want all of you to do on your screen, whatever type of screen that you're using, I want you to stick your fingers in front on top, and I want you to stick your fingers up. And you'll notice that your thumb is pointed over here when you stick it on top there, which means that this is north and this is south. So that means that our magnetic field would run from north to south like that in that direction. It's the same thing on top. It would run from north to south. So I'm just going to give you a second to try this. Just remember that the small line is negative and this positive. And Mr. Worldwide can help us. And Mr. Worldwide tells us that our current runs from negative to positive, right? So we can see this is a 3D picture, and the current is running up here, and it comes behind, so it'd be moving down here, and then it goes around the back, and then it goes down here, and then it runs around the back, and then it runs down here like that. So you can see in front of them, all our currents are pointed down. So stick your fingers in front, and you can see that if you put your fingers downwards, that your thumb points over here. This is the north end, this is the south end, so we can figure out the north and the south end of our magnet. So find the direction which the current would go. So now they've given us the direction of our north magnet, and we want to know which direction is going to go across the ammeter. Is it to the right or is it to the left? So I'll just give you a second to sort of try it out and think about it. So since you can pause this video if you need to, I don't really need to give you that much time. So point your thumb over towards the north end, right? And you can see that when you're in front, your fingers are all pointing downwards here, right? So that means that that's the direction of the current. The current is going down, and when it goes behind, it loops up, and then it comes back down in front. So that it tells us that it would go across the ammeter in that direction there, right? That's how we would get it to work. So this stuff is just kind of fun stuff, but we don't really need to do fun stuff in this. So I'm just going to skip this, and you don't have to worry about this. You won't be tested on it. You won't be tested on this video. So just extra stuff. So our last board question is, now I want you to draw in what direction a compass would be pointing in all of these circles here. So it would be pointing up, right, left, down in all these situations, right? So you can see that the current is moving upwards here. So you just kind of have to trace that current around. And again, I'll give you a second to sort of try it on your own, and then I'll give you the answer. Okay, and again, since you can pause it, feel free to pause it if you want to try for a little bit longer. So you can see that if I follow it, it's going downwards, and then behind it's going up, and then in front it's going downwards again. So I would stick my fingers downwards, and I would be able to indicate that this is north and this is south. So my magnetic field always runs from north to south. So my compass, the north end of my compass would be repelled from the north end, and it would follow these lines. It'd be going that way, there, and then it would be pointed direct towards the south. And it's the same thing on the bottom. It still runs from north to south, right? It still goes from north to south in that direction. Oops, I drew it backwards, sorry. It runs from north to south in that direction, sorry, my bad. So the compass would be pointing that way. So it should always be the same on the top and the bottom. So I have one last question for you. If I placed my compass inside, which direction do you think you would go? Right? It always runs from north to south, so it always goes in this direction. So the weird thing is that it would go opposite of what we drew here. So it would continue in a loop, and then it would be going that way. So they always go in a circular pattern like that. So inside, it would be going to the left of your screen. Okay, and that's pretty much it for this lesson. So we're going to start off nice and easy. So that's our homework on the second left-hand rule. Question 7, question 8, question 9, question 10, and 11a. And that's it. So start off nice and easy, review some of the first left-hand rule, and that's it. So thanks for listening, and that's it from me.